Hi, I'm Lee Tushler, Executive Editor of Design World and EE World.
And I'm Kelsey Ferrante, Associate Editor. Today we've got another smart LED light bulb to look at. It's called the Tradfri, and it comes from the furniture maker Ikea of Sweden. It's now available in Europe, but we're not really sure whether it's come to the US quite yet. It has its own remote controller, which can set the bulb's color temperature and dimming level.
As smart LED bulbs go, this one's pretty simple. It doesn't use any sort of smartphone app, and it can't be controlled over the internet like some other smart bulbs we've seen. It just works with a remote controller that comes with it. The remote controller is just a 5-position switch.
Perhaps the most interesting thing about the remote is how it mounts to the wall. In that IKEA has a reputation for quality furniture, it's probably not surprising that the remote has what seems like an elegant mounting scheme. A base for the remote mounts to the wall either with screws or adhesive. Then the remote itself is held to the base with magnets. This scheme lets you remove the remote to change its battery when the need arises and gives the wall-mounted remote a sleek look. The battery is a CR2032, a widely available 4.3-volt lithium coin cell.
The IKEA bulb implements its wireless capabilities strictly via Bluetooth. It doesn't use Wi-Fi, as a few other smart bulbs do, and the Bluetooth is added to the LED bulb the same way we've seen it done in other smart LED bulbs. The designers use a separate circuit board that holds the wireless chip, and one edge of this board is soldered to the main board holding the driver electronics. What's kind of interesting is that the identical wireless board also resides in the wall switch. The wireless chip in both the LED bulb and the wall remote is from Silicon Labs in Texas. It's a Bluetooth system-on-a-chip device that includes a 32-bit ARM controller, a radio transceiver, I/O ports, and serial interfaces, as well as a bunch of other peripheral functions. In fact, the chip integration is such that there really isn't much else on the wireless board besides a printed circuit antenna, which pokes out through a hole in the LED plate. One interesting thing about the wireless board, though, is that we can see there are only 6 soldered connections between it and the rest of the LED driver board. If power and ground account for 2 of them, that means there might only be 4 leads available to control the LEDs, unless the designers are doing some kind of weird multiplex thing on the leads.
And the wireless board on the remote was the same as on the bulb?
Looks to be the same. Though we have no way of knowing whether the Silicon Labs chip is identical, since system-on-chip devices can be made with a variety of different options. On the wall remote, the Bluetooth board mounts flat on the main circuit board. The main circuit board primarily holds the wireless board and a battery holder, which serves as a substrate for the switch pad. The switch pad itself is a straightforward conductive rubber design where pressing a switch pushes down on a conductive rubber contact that in turn touches the circuit board to signal a button push. But all the magic happens on the Silicon Labs chip. The only other components on the main board are part of the interface for the conductive switch.
And that brings us to the architecture of the LED bulb.
Right. The bulb itself has an architecture that's widely used for LED bulbs. It employs a 2.4-ounce heatsink that surrounds a circuit board potted in flexible epoxy-like material. The epoxy also provides some structural rigidity to the base of the bulb and the electrical contacts. The main circuit board and all the epoxy potting material fits inside a plastic sleeve that, in turn, fits inside the heatsink.
The LEDs on the bulb reside on a single metal plate that probably doubles as a heatsink, but the LED plate looks a little different than the others I've seen.
Right. This is the first LED bulb we've torn down that uses connectors to make a connection from the circuit board to the LED plate. The usual way of connecting the LED to the circuit board is through the use of 2 wires that are just soldered to the plate and to the circuit board. This IKEA bulb, though, uses not 1 but 2 connectors to make the electrical contact between the circuit board and the plate. Physically, each connector takes the form of 2 pins extending from the main circuit board that mate with a single contact on the LED board.
Why 2 connectors instead of just 1?
Glad you asked. The reason the bulb uses 2 connectors rather than just 1 seems to be because the 28 LEDs on the bulb are wired as 2 separate strings. That's different than what you normally find. Most bulbs just wire all their LEDs in series in 1 long string.
So why put them in 2 different strings?
Well, if you take a close look at the LEDs on the plate, the reason for the 2 strings becomes clear. there seems to be two different kinds of LEDs on the plate. One style has a slightly darker amber color than the other. The darker LEDs are in one string on one connector. The lighter LEDs are in the other string and are wired to the other connector. So the two strings evidently can be operated independently, and that's probably how the LED bulb manages dimming and changing its color temperature. It judiciously lowers or raises the current to the two strings as a way to modulate both the amount of light output and probably the color temperature as well.
How are the two strings powered?
Well, interesting question. Because most LED bulbs only use one string, most LED driver chips that are designed for use in LED bulbs are also only set up to handle one LED string. So when the bulb has two LED strings, as in the case of the Ikea bulb, it can't really use a driver chip designed to handle just one. On the other hand, there are indeed a lot of chips out there designed to drive multiple strings of LEDs. Problem is that the applications most of these chips address are in LCD backlighting or related display type uses. They really aren't set up for light bulbs, so they really aren't appropriate for what Ikea is doing with this light bulb.
So if most LED drivers won't work for this bulb, what did IKEA end up using?
Well, judging by the chip markings we found, the LED driver isn't a standard device. It's an 8-pin chip that seems to be custom made. Our guess is that it's based on somebody's standard LED driver design that was modified to handle two LED strings. But we can't tell who made the chip based on its markings. But what we can do is look at the other components on the circuit board and make some guesses about the driver topology. Starting with the primary side of the circuit, we think it's noteworthy that you find 5 large capacitors near the diode bridge and a power transistor, but no inductors. That might mean that the transistor is there for purposes of power factor correction. And most LED bulbs these days do in fact incorporate some kind of power factor correction, though we couldn't find any power factor specs for the Ikea bulb. The fact that there are no big 60 Hertz inductors in the primary side of the circuit tends to eliminate the possibility that power factor correction takes place passively. Most passive power factor correction circuits use bulky inductors, and you just might not have enough room in the base of the LED bulb to hold them, along with everything else that has to fit in there. And that's why most of these bulbs go with active PFC if they do it at all.
I see a big transformer on the circuit board. What does that do?
That is part of the driver circuit itself. To figure out what kind of topology we might be dealing with here, we note that the circuit on the other side of that big transformer consists of identical pairs of components, as you would expect to find when there are two channels of LEDs being driven. The circuitry for each channel includes a power FET, an inductor, 2 big capacitors, couple sizable diodes, and a 6-pin chip too small to be identified by its markings. The fact that you find dual sets of these components confirms the idea that the two LED strings are independently driven and controlled.
So where does that leave us in terms of figuring out the circuit?
What seems to be happening here is that the big transformer is there basically to isolate the secondary side of the circuit and to divide the input power into the two portions used by each of the LED strings. The DC conversion and development of a current source for driving the LEDs seems to take place in the secondary side of the big transformer. To figure things out, the question we have to ask is, what kind of a converter could employ an FET, diode, inductor, and capacitors as its main components, because those are the chief components we find in the LED string driver? And the answer would seem to be a buck converter. This topology steps down voltage while stepping up current, and it typically contains at least a diode and a transistor and at least one energy storage element, such as an inductor. To reduce the voltage ripple, it might incorporate a filter comprised of capacitors. So the buck converter would be our guess as to what we're dealing with here.
With that, we've reached the end, but I think we have time for one light bulb joke. How many computer programmers does it take to screw in a light bulb?
I'm at a loss.
2, because one always leaves in the middle of a project. And if you want to see more teardowns like this one and hear more jokes like that, just go to designworldonline.com or eeworldonline.com. Thanks.